We come now to one of my favorite topics in mathematics, the notion of inverse function. At a basic level, we are investigating the question of, given a function, can I find a new function that undoes it? That is, can I take the outputs of my function and reconstitute the original inputs? This is a question of great significance throughout the quantitative world, especially in mathematics and physics. We will just focus on a few basic examples and introduce some terminology and techniques for determining when you have an inverse function or not. So let's look at the mathematical definition. Given an initial function f of x, we are interested in understanding when it has an inverse function. What does this mean? It means that the function f inverse, that's how you say this, should satisfy so this thing here, of course, is composition of functions, which means that I have f inverse of f of x. That should be equal to f of f inverse of x, and that should output x. So in other words, f inverse undoes f. So it's a way of saying, given my outputs, how do I recover the inputs that I had? Right, so just to make a few remarks, one is about notation. The common notation, of course, is what I just wrote, having a little -1 in the superscript of your function. This should not be confused with (1 over f of x). Having a -1 involved makes it look like maybe you're raising it to the -1st power, which would correspond to taking the reciprocal. That is not what we're doing here. We're doing something different. Okay? The reciprocal would essentially give you an inverse in the sense that f of x times 1 over f of x equals the function 1. Here we're looking to compose the functions. We're looking for a function that returns your original inputs given the outputs. But the notation's a little weird. Right, and then a remark on something we've discussed earlier in the context of exponentials and logarithms. So I'll say recall conversation on a to the x and log base a of x. That if I have a function with a given domain, the range of its inverse function will be that domain, and vice versa. So taking inverse functions requires switching domains and ranges. So this is a nice way of kind of testing theory for these things on the CLEP exam. Okay, so let's look at a technique for determining whether an inverse function exists. It's quite often the case that a given function with a formula or a plot will not have an inverse function. So what matters here? How can I tell whether a function has an inverse or not? Well, just like how we had a vertical line test for testing whether you had a function or not, we have what's called a horizontal line test for determining whether or not your function has an inverse. So what we do is we take the plot of the function f of x and we draw horizontal lines. So the function has an inverse if every horizontal line intersects the plot at most one place. So here in the plot on the left, I have an example of a function where every horizontal line intersects my function only once. So this is an example of something that passes the horizontal line test. Which tells me there is an inverse. Conversely, the plot on the left is a parabola. This fails the horizontal line test. Most horizontal lines intersect at 2 places. For example, here and here. So this fails the horizontal line test, implies no inverse function. So what I'd like to do now is look at a few examples We'll use the horizontal line test to determine if there's an inverse function. And if there is an inverse, we're going to try to find it. We're going to try and find a specific formula for it. Okay, so let's start with f of x equals x squared plus 1. So to use the horizontal line test, we want to have a plot. Let me check. I drew a little parabola to represent my function, and almost every horizontal line intersects at more than one place. What do I conclude? I conclude that I fail the horizontal line test. Which implies no inverse function. Sad. Okay, let's look at another example. F of x equals log of x minus 2. So again, kind of intimidating looking. But if we use our basic idea of what the logarithm plot looks like, and then our rules for translating, it's not so bad. So I am translating to the right by 2. So the picture is something like this. And I ask myself about the horizontal line test. Do I pass it or not? The answer is yes. Every horizontal line intersects only one place, which means I pass the horizontal line test, which means I have an inverse function. So how do I actually compute it? Well, the standard trick for this is to take my original function and switch the roles of the input and the output. So I'll write this as y equals log of x minus 2. And then I switch the roles of x and y so that x equals log of y minus 2. And now I solve for y. So essentially, I pretend that the inputs were the outputs, and I try and solve for the new thing. So now I'll say, how do I kill off this logarithm? I exponentiate. So I get 10 to the power x equals y minus 2. So y equals 10x plus 2. Of course, this is the common logarithm, so base 10. Okay, so of course, the inverse function to a logarithm I've alluded to, it's exponential, and that's what we see here. This logarithm has an exponential inverse function. One more that's actually a bit simpler, just a nice line. Okay, so here's something like my plot. And now I ask, does it pass the horizontal line test or not? So I draw some horizontal lines. It appears to pass. Okay, so the inverse exists, and how do I find it? Well, I write this as y equals negative 2x minus 1, and then I play the same game where I switch the roles of x and y, and then solve for y. And it's just that simple. So there's two things you want to take away from this lesson. What an inverse function is and how to identify it, and then what I just did, which is how to actually compute it. Right? So there's sort of the theoretical piece, which is what is an inverse function and how do I use the horizontal line test to theoretically establish the existence of an inverse function. But then we also have the computational aspect, which is once I know the inverse exists, how do I get my hands on it? Well, in this case, it worked out rather nicely. In the examples we looked at, we could just switch the roles of the input and outputs and solve. In general, there's a huge mathematical gap between knowing the existence of the inverse function and being able to find its solution. There are many mathematical questions for which it is known that an inverse exists, but getting precise actual algorithms to compute the inverse is quite hard. So it might seem like it's straightforward to go from the theory to the computation in these cases. But as you move up in this world and learn more complicated mathematics and science, you'll realize sometimes the theory doesn't translate quite as well to practice.